So, before we get on to talking about Pride and Prejudice, first off, I'm going to talk about breakfast cereal. My children, for some reason, demand food on a regular basis as much as 3 times a day, for some reason. So, if I wanted to start compiling some statistics about my kids' breakfast cereal habits every day, because what sort of a weirdo would go around writing down what the kids ate every day for a month? Me. But we could start to collect some data about what they do. We could start to try and put together a model of their habits. Bear with me, it'll all become clear. Now, what we notice here is, of the 3 cereals that they have to choose from, they seem to have a little bit of a preference for Cheerios there and for Cocoa Pops compared to some of the others. They also, you will notice, tend to be a little bit faddy. They tend to have their favorite and then stick with that favorite and then move on. Fine. Interesting. So, some very simple statistics. Clearly, they, in fact, prefer Cocoa Pops. They took that 11 times out of the month, compared to 10 for Cheerios and 9 for Weetabix, poor old Weetabix. So if we wanted to create a really, really simple, dumb model of how to represent this, yeah, I'm not very good at drawing, we could do something like this. Just literally, day by day, we could say, we know the distribution, we could just make a simple, dumb choice every single day. And by and large, we get something statistically that about matches the original source data. And if you try, you end up with something like this. Every single day, I have literally rolled the virtual dice and tried to generate another month's worth of data based on what I had in the old stuff. Problem is, we've lost something using this model. We've lost the faddiness. These virtual kids here that I've created are nowhere near as faddy as the ones that existed in the real world. These guys are much more likely to just simply switch from choice to choice each day. So what I want to do is find a way to model this, but keep the actual underlying structure of the data. So if you think about it, we've actually got 3 states: Cocoa Pops, Cheerios, and Weetabix. And for each of those states, 3 possible things could happen. They could stay the same, or they could switch to one of the others. Those are the, in total, 9 things that could possibly happen at any given point. If then you create some statistics based on that concept of, given we are Weetabix, what is the chance that we switch to Weetabix again, to Cocoa Pops or to Cheerios? Given that we are Cocoa Pops, what are the chances that we stay the same or switch? And so on. You end up with something, with a statistics set that looks more like this. And what we have captured here is a little more information than we had before. For example, notice that the kids never switch from Cocoa Pops to Cheerios, ever. Is that significant? I don't know. Could be, could be not. I've only got 1 month's worth of data, so it's not an awful lot to act on. Still, same. It could be significant. See, same. Cheerios to Weetabix never happens. And we get some sort of idea of how faddy they tend to be on each thing. They're not as faddy on Weetabix as they are on the other 2 cereals. Although, interestingly, they are equally faddy when it comes to Cocoa Pops and Cheerios. There's it represented as a probability percentage. So if we remodel now, based on this idea of state switching, what we end up with is something like this. This is based on the idea that I arbitrarily chose Weetabix as my first choice. And then based on Weetabix, I said, what were the chances of going from Weetabix to whatever? Let's make a random choice. And then so on, day after day, each day. And then what we do is we generate a set of data which looks more like the original. We've captured that faddy tendency to stick with one thing over time. There's a load more maths behind this. I'm going to skip this because I'm doing the quick version today. But this is what's known as a Markov chain, invented by this gentleman, Andrei Markov. He was a Russian mathematician with one of the most fabulous beards I've ever seen in my entire life. And he described this in a paper way back at the beginning of the 20th century. This stuff is really flipping old, but still very much in use today. So a Markov chain is a model of a behavior of a continuous system which has certain properties, which are as follows. they're discrete, meaning you are state A, state B, or C. You cannot be A and B or B and C. You can't be any combination of them. It is one or the other exclusively. We are only modeling the changes between states. That's the only thing that we're interested in for the purposes of capturing information. And this represents the complete set of states for the system. If in my imaginary breakfast cereal case, there is no possibility for the children to choose cornflakes. That simply doesn't exist. I have captured all states and their probabilities, even if one of them is never selected. It doesn't matter. And it has no memory. That's a very important concept with this. It literally knows what I am doing now, what I will do next. It has no memory beyond that point. So moving back to, so moving on from our serial, how can we apply this idea to Jane Austen? Easy peasy, here she is. This is the only image of Jane Austen ever drawn from life, believe it or not. Sketched by her sister, and I'm hoping on that day she possibly had been sucking on a particularly sour lemon, or that maybe her sister wasn't the greatest of artists, but there we have it. Or possibly poor old Jane is sad because she only ever wrote 6 novels. And I know there's only 5 pictures here, 2 of them were published together. And I'm not counting the novels that she never quite finished, but come on, 6 novels, that's all she ever wrote. So can we help her with that using Markov chains? Yes, we can. This is the opening of Pride and Prejudice. It is a truth universally acknowledged, blah, blah. We've probably all heard it before. So what if we were to treat each word as being a single state? Okay, so first, let's treat the word it as a state. Great. So to generate Markov chains, we need to then find all instances of the word it in the entire novel, that being Pride and Prejudice, and work out what it was followed by. So 82 times it was followed by the word was, 72 times it was followed by the word is, and so on, down to, there's actually 235 possibilities there, most of them only single instance. But using that, we could create some sort of model that will randomly select one of those options given the word it, weighting it appropriately based on which is the most likely candidate. So for the sake of argument, I'll just go with the most probable option, that being was. So then we could go and find every single instance of the word was in the entire book. As it happens, every single instance the word was followed by a different word 1,843 times. So that would be a straightforward random selection of one of those words. Easy. If you do that, you end up with something like this. It looks fairly reasonably like a big block of Jane Austen's text. It is not perfect, though. There's a little bit of pre-processing needed in order to make this model work a bit better. If you notice, it gets a bit confused with full stops. Are those abbreviations or are they the ends of sentences? We've got random instances of words like Bennett without being preceded by the word Mr. or Mrs. There are some anomalies, and there are ways that we can improve this. And one of those is by treating each pair of words as a state rather than a single word. I'll briefly just show you the code that I use to generate this, and hopefully that'll give you an idea of how relatively simple this is. So start by reading in the complete text of Pride and Prejudice, which I took from projectgutenberg.org, which incidentally, this is the most popular text on the entire website by quite a long way, which is why I chose it for this particular little silly demonstration. Then, having read it in, I've replaced each punctuation mark with the same punctuation mark with a space either side of it. Why that is, I'll get to it in a second. Then I've split on new line. So we've now got an array of each line for each paragraph in an element from the entire book. And then I'm adding an arbitrary symbol at the end to indicate that this is the end of a paragraph, because as you'll see in a minute, we'll quickly lose where the ending of paragraphs goes. I've arbitrarily used the BR tag from HTML. You could use absolutely anything you like as long as it's unlikely to otherwise appear in the text. Then we split on the space. This is where we start to lose track of, and I'm using a select many, so I'm merging all of these arrays for each paragraph into one gigantic array. This is why we needed the BR tag to make sure that we could track where paragraph ends go, and then stuff this whole thing into an array. So we've got every single word and punctuation mark and a character to indicate new line in the entire book in one single giant single dimensional array. There's the magic that does the chaining. I'm not going to dwell an awful lot on that. Most of you could probably recreate this with a little bit of imagination. But the principle is that I am taking two-word pairs, moving one word at a time. So start with it is, then move to is a, then move to a truth, and so on. So, and then looking for every instance of that exact two words occurring again in the text, and then counting what it was followed by and how many times. So it is was followed by the word a 13 times, the word very 3 times, and so on. So we've gotten ourselves a great big block of statistics. Takes the computer a little while to compile this, depending on the power of your processor, but that's fine. You could dump this if you wanted to create many of these. So then I convert it. I convert each one from this array structure with the number count to, I'm using enumerable.repeat to literally repeat any given word the number of times as appropriate, depending on how many times it occurred. The reason I'm doing that is that I want to make selections simply, and the simplest way to do that is to literally have an array of all the options and then select create a random integer to select one of those. And if I've repeated a the number of times statistically that's appropriate, then statistically I'm going to get a that number of times as we would expect. And then all I'm doing is looping through this. I've stuffed all of this into a dictionary structure because I love dictionaries. Dictionaries are cool. And my limitation on how long we go is how many paragraphs we've encountered, how many BR tags. I've chosen here 500, which they're as good as anything. You could go on for as long as you like or as short as you like. You could write 2 million and it will happily generate you Pride and Prejudice content for the next 200 million paragraphs, however many you select. But all I'm doing is take 2 words and use that in the dictionary structure, use a random number to select one item out of the array attached to it, select that as the next word, then select the second word out of the pair you are on and the new word, make that your new pair, and carry on again and again and again forever. And then at the end, replace any BR tags with simply 2 new line characters to restore the original paragraph breaks. And this is what you end up with. And this actually looks fairly reasonable. We've got most of the structure that we want in place. We don't have the confusion with the full stops. This actually looks fairly reasonable. It still gets a bit confused sometimes in certain circumstances. And of course, the biggest problem is that it's utter gibberish. You know, there's no memory in the structure of the algorithm I'm using. It forgets what's going on one word to the next, so characters will appear and disappear with no special meaning. It won't always remember to close all speech sections with a speech mark having started them. Frankly, it won't even know that it's speech or not. There's no memory in the system. All it's doing is creating something which statistically is identical to the original text from fresh. This is the equivalent of taking Pride and Prejudice, running it through a meat grinder, and then sort of spewing out whatever comes onto the page. Now, that was all good fun, and I have some recordings somewhere of an actress reading this out in the proper Jane Austen voice, and it's frankly hilarious. Then that's all good fun, but what's this actually for? This is a representation of Google's PageRank algorithm. I don't understand it, I'll be brutally honest. Probably you need several degrees in order to, because it's Google's PageRank. But the principle is that it uses Markov chains to make a decision on how high to rank a page based on how many ways a particular URL can be reached from other pages. And I'm sure there's a whole load more to it, but still, at its core, it is still Markov chains. This is predictive text message on your phone. Once again, probably a few extra rules, but fundamentally It's still Markov chaining. It's crunching down everything you've ever said in the past, and then based on that, it's selecting out the most likely thing that you'll say next. Making marketing. You can use it to crunch numbers. So you don't just have to use this to be generative. You could just crunch the statistics, and then there are various techniques which I don't have time to go into for this session, but you can generate graphs based on that will tell you things like, in the instance of my kids, it would tell you things like what statistically is the cereal that the kids are most likely to select, given the possibilities for chaining between the three different states. You could use this for predicting future trends for your customers and for making orders of stock based on what is the most likely to be required. Predicting the future. Slightly less in person than these gentlemen did it, but still, you could use it to see what's likely to be happening in your environment going forward. Testing, I would imagine, will be a good one. If you wanted to have a long stream of live-like data which statistically matches the source, but isn't just simply a recreation of that, you could have Markov chains running, which will churn out as much test data as you want forever until you stop it. And of course, you could use it to make Jane Austen happy, as in this slightly better drawing based on the original. Any questions at this point? I'm aware that I've possibly overrun slightly, but still, if anyone has any questions, throw them now or else grab me in the chat.